Right. Good afternoon. Good afternoon to everybody. Welcome to this presentation. My name is Fred Nichols. I'm from the Department of Electrical Engineering at UCT. I'm an associate professor in the department and currently the head of the department. And welcome to our virtual open day. And I'm going to start off with a presentation. Let me share my screen for you. All right, just a quick look at what it is that we are going to be doing over the next while. I would like to basically take you through a description or an introduction to the discipline of electrical engineering, what it is and what electrical engineers typically do in the outside world. We want to take you over a quick tour of our department, obviously a virtual tour, and then we're going to move into questions and answers where you can sort of clarify any concerns or information that you would like to have from us. Right, so the topics I want to discuss is what is electrical engineering, what would you do as an electrical engineer, where do electrical engineers work, and what kinds of skills do electrical engineers basically require, and I guess those are the skills that we as a university would develop in the students that come into our department. And then, as I said, the virtual tour will give you an idea of what the students currently in our department do on a day-to-day basis and how we embark or engage in the academic endeavor. Right, so what is electrical engineering? It's quite a difficult question to answer because it's a very diverse field, but traditionally, electrical engineering would be the study and the application of electricity, electromagnetism, and electronics. And I've put together a little bit of a montage of the history of the origins, I guess, of electrical engineering as a discipline. And it is in the late 1980s that really people started to begin to understand electromagnetic radiation and how it could be harnessed and used for, I guess, for the benefit of mankind. Many of these images I've taken are actually of Nikola Tesla, who was one of the first innovators to work in the field of electrical engineering. This is actually a fake picture on the left of I forget the name of the system that he was working on. But he had a lot of ideas about how to generate large-scale electrical systems transmitting electrical signals, and more interestingly, he was very interested in transmitting electrical power. So this is a picture of his Wardenclyffe Tower. He was a well-funded individual. He had a lot of patents and he had a lot of money thrown at him by various sources. And he had the capacity and the resources to build big devices like this to try and actually get an understanding of how to apply electricity in the modern world. It also turns out that he played with X-rays. If you guys have done physics, electromagnetic radiation spans all ranges of all possible frequencies, and it also spans the frequency range of X-ray radiation. So he also he didn't invent X-rays as an imaging technology, but he certainly was right up there with the people that did. I've also shown another picture of the origins of electrification. So Thomas Edison and, for what it's worth, Nikola Tesla, they were competing in some ways with their technologies that they preferred. And there was a big fight at the end of the 1800s about whether alternating current or direct current should be the mechanism or the method used for distributing electrical power. But that was also the time at which lighting systems started to be developed. Prior to electrical lighting, most cities were equipped with gas lighting, although I guess those that were fortunate enough to have any lighting at all. And the development of the electrical light bulb was quite an interesting story. It has an interesting history that goes back quite a long way. Over here I'm showing the spark gap transmitter. That was the first indication that electromagnetic radiation in fact exists. So James Clerk Maxwell postulated that it existed based on theoretical physics. Basically, it's the same physics that Einstein developed in the special theory of relativity. So Maxwell postulated that EM radiation existed, and Heinrich Hertz built the first spark gap transmitter that actually was able to use this to transmit electrical signals through free space. And basically a spark gap, it just involves accelerating electrons or charged particles. And whenever a charged particle is moved in space, it generates an electromagnetic radiation or electromagnetic pulse that propagates through space. So this thing actually turned out to be like Morse code. They couldn't modulate signals onto it, so they couldn't modulate speech onto it, but you could essentially have impulsive bursts that would give you information, or that you could use to convey information. So that's the sort of the distant origins. Around about the 1940s, Bell Labs developed the transistor, which was a game-changing device. So this is one of the, it's a mock-up of one of the first transistors. And that completely has changed the face of society as we know it. The semiconductor revolution and all the computing devices that we know today basically came out of that story. So that's the traditional view of electrical engineering. But electrical engineers nowadays are far broader than that, and many of them actually don't work in electronics or don't work directly with electromagnetism. So in the modern society, power engineering and power distribution and generation is a massive subject. Control, how to manipulate, or how to make machinery do what you want it to do, how to make robots do what you want them to do. That whole discipline involves feedback. It involves being able to measure things and actuate things and make sense of a signals description of the world. And that's very much in the domain of electrical engineering. I've mentioned a little bit about electronics. When I was younger and I said I was an electrical engineer, the question that often came up was, can you fix a television set? And the answer is no, I can't fix a television set. But interestingly, I could probably design and build a television set. So engineers aren't necessarily right at the low level of being conversant with the minutiae of the discipline, but they've got a broad picture of how things work and how to make them do what they want them to do. Microelectronics, so electronics and microelectronics. Transistors have got a funny property that the smaller you make them, the better they work and the less energy they use. They become more efficient and they go faster. So the drive towards making things smaller is quite important. Also, we want our devices to be small. So small-scale electronics is really an important thing. Then I've mentioned signal processing. I mentioned it a bit in the context of control, but signal processing involves measuring things in the physical universe or in the physical world, and taking those measurements and turning them into information. So some of the measurements that we see or some of the information that we have in the world might be, for example, radio broadcasts. It might even just be image data or video data, which is a subject that I work in. So a video is a signal and you're able to do things to it in order to extract information from it. Telecommunications, I think everyone is familiar with cell phones and that side of things, and it's a big industry with lots of useful purposes. The whole world is becoming connected, and basically it is our future. Instrumentation, I think I've got a couple of slides that I'll talk about these a little bit later, but we can go into detail when I come up with those. And computers, the whole modern world revolves around computing devices. And our electrical engineering graduates are very, very conversant with computing and computing hardware, how to design and build computing hardware, and how to program computers to do the things that we need them to do. So electrical engineers and computers are very, very closely tied to one another. And in practice, electrical engineers would be the people that build computers to a very large extent. And then there's sort of hybrid disciplines, mechanical and electronic. So the world is a complex place nowadays. You can't just have expertise in one discipline and actually hope to make a difference to the world. So combining mechanical engineering and electronics is an important interdisciplinary branch that's slowly emerging as time progresses. All right. So what do you do as an electrical engineer? Well, ultimately, you design and you develop and you test and you manufacture mostly electrical equipment and electrical systems. And I've put electrical in brackets because engineering is a very generic discipline, and the skills that you have aren't exclusive to electricity and electrical systems. So we would be able to, a practicing engineer should be able to work in other disciplines, but primarily the base of the discipline is in the electrical side of things. So what does this mean to you, and where have you seen these kinds of things? This is a 5G cell phone tower. It's the new way of connecting. The fourth industrial revolution is basically the automation of manufacturing and the networking of many large-scale connection of many devices. And in order to facilitate that connection between literally millions and possibly billions of devices, we need to have very good infrastructure for telecommunications so that they can have a network to talk to one another with. And that's ultimately the goal of the 5G system. Incidentally, 5G towers don't cause COVID, but they do provide very advanced telecommunications capability, mainly on the data side, for networking the world. This over here is Apple's new iPhone XXX. No, I'm just kidding, obviously. It's one of the first, let me get the details because I found them quite amusing. It's one of the first cell phones that, I guess it might not be a cell phone, call it a mobile phone, that was ever developed. It's the Motorola Dynatec 8000X. It weighed 1 kilogram, it's 33 centimeters high, it can remember 30 telephone numbers, takes 10 hours to charge, and it gives you 30 minutes of talk time. And it costs $10,000 in modern day money. So that's where we started, and I think you all know where we've basically ended up. That whole revolution, everything about the telecommunication system, basically is something that an electrical engineer knows lots and lots about. The picture I've got over here is the new manufacturing revolution, essentially 3D printing. This is a 3D printer that's able to print large things like cars, for example, and it seems that's our future. Instead of having bespoke production lines, we can actually have general purpose devices that can do a lot more for us, or general purpose equipment that can do a lot more for us. Self-driving cars, they're coming. The days where you park your car in a parking lot and spend your day doing something and then go back to the parking lot and drive your car home is probably soon to end. It makes a lot more sense to order a car, drive to where you want to, let the car drive off and carry the next person around. Self-driving cars, much of the technology is electrical engineering. And here we have a self-driving boat that was built in our department, and ultimately that's part of our endeavor to try and build autonomous systems for monitoring and exploring the Southern Ocean. Another example of the technology, the square kilometre array. It's a massive, massive radio telescope. There's a demand in physics to be able to look at the natural universe, to look out into space, where ultimately the further you look out in space, the further back in time. You could look at the start of the universe, see where it comes from, and actually uncover fundamental physics. So in order to do that, a project started about a decade ago to build many radio telescopes. The idea is that they're widely distributed. I think the Southern African version starts in the Northern Cape and goes right across to Mauritius. But there's also some in Australia. So it's a massive, massive distributed set of radio telescopes, which essentially are just antennas, dishes. And the ultimate goal is there'll be 1 square kilometre of dish area looking at the sky and actually providing a wide baseline interferometric system for making pictures of the universe. This is one of the pictures made by Meerkat, which is one of the radio dishes that forms the SKA. That's our galactic center over here, and it's producing fantastic data. But now you've got literally thousands of these dishes distributed across the world, and they're having to deal with humongous amounts of data, and very high performance computing is required to process that data in real time. So there's a huge hardware requirement to be able to process the data. The back-end networks for the SKA, if I'm not mistaken, they transfer as much data as I think the entire internet used in 2013. So the requirements, the sort of the computing and network requirements for this system are phenomenal. And a lot of that is driven by electrical engineers who know how to work with radio waves, they know how to work with antennas, they know how to work with computers, and they know how to work with networking. And my third example that everyone probably is familiar with is our electricity crisis that we have in the country, and driving around in the dark is something that is happening quite a lot. It actually happens quite a lot in the third world, where electrical infrastructure isn't properly funded or isn't properly run in some way. So Rolling blackouts are a fairly common phenomenon around the world. It's not just South Africa that experiences it. Here I've got a picture of the Great Northeast Blackout in the United States. I think that was in 2003, if I'm not mistaken. I should probably keep my notes. But ultimately what happened there was, I believe the power lines dropped onto some foliage, onto some bushes, and the software that was running the electrical system had a software bug. And the software bug didn't recognize what was happening, and it responded in the wrong way, or it didn't respond in the right way. And it actually generated a power outage that took out 5 states, I think, in the United States, and it took out parts of Canada as well, purely on account of a software bug. Another instance of rolling blackouts is quite interesting was the California electricity crisis, also a few years ago. I think that was in 2001. And that was caused by a completely different thing, but California had rolling blackouts for almost a year, I think. And it was caused by deregulation, where the government basically put the power of the electricity supply into the hands of the companies that ran the electricity supply. And those companies realized that if they carefully turned off a couple of power stations every now and then, they could they could drop the supply and thereby increase the demand, and they were allowed to change their pricing according to demand. So they could drive the electricity price up through the roof. I think they drove the price up by a factor of 20. So they basically turned off sections of California to make lots and lots of money, and California just had rolling blackouts over an extended period of time. Anyway, so electricity crisis is a big thing, and it's a universal thing in the world that we have to deal with. And that basically leads to, I guess, one of the resolutions of the electricity crisis is the whole renewables revolution, which is very firmly grounded in electrical engineering. The power crisis is probably the most important crisis that South Africa and the world, I guess, in some ways is facing. And being able to harness the power of renewables, these are wind turbines over here, solar power, all the rest of them, being able to harness those things provides a different source that is future-proof. We will run out of coal. There's no doubt about it. We'll run out of all fossil fuels, but we're not going to run out of sunlight or the things that sunlight powers that we're able to harness. So it's just a question of when we run out of fossil fuels, not if we run out of fossil fuels. And the future clearly lies over here, and that's an electrical engineering discipline. I suppose this whole thing is an electrical engineering discipline. But this is the old school, this is the new school. To some extent, we could solve the whole load shedding or rolling blackout problem in South Africa by just signing a proclamation that says people can provide renewables. And I think there's 5 gigawatts of renewables waiting in the background to make that happen. But we can't do that for various political reasons. All right, so what else do electrical engineers do? Well, a typical consulting engineer would plan projects, estimate the time and cost of that project, manage and test implementations, and ensure that everything is safe so that people don't die. Work in transport, lighting, heating, ventilation, power generation, and so on and so on. Where do you work as an engineer? Well, you can work on plants or you can work in offices. Sort of, it's up to you. Laboratories, laboratories, universities, research facilities. I'm in a university. Research facilities look more at sort of development of core functionality or core capability. I've mentioned power generation and the transmission side of it. Engineers, electrical engineers also work in construction, factories, mines, production plants. They're involved in railways, aerospace, airplanes. Every airplane's got a very complicated control and electrical system, and cars are going the same way. I've mentioned telecoms and IT. That's the whole cell phone and internet, internet technologies. And our graduates can also do technical innovation, gaming, software. We're very good with computers. So we can work as software developers if that's a place that we end up needing to go. And finally, engineers are very diverse. I've got a lot of graduate students that work in finance and hedge funds and derivatives. The skills you acquire as an engineer are very, very transferable, and they can apply to a lot of different industries. Logistics, engineering services, and general management. Engineers, because they're so well trained, they can actually work in just about any setting, and they're very good at taking an overview of a situation and managing to manage that situation to work better for them. Right, and we make transferable skills. We use specialist knowledge to creatively and innovatively solve problems. And it's that problem-solving aspect that we try and develop in our students. Turning practicality or practical skills to turn concept into reality. Take an idea. What do you need to do to make something happen from that idea? Those are skills that we also really try hard to further in our student cohort. Effective communication is essential. Team working is a part of the engineering discipline. Nobody can do a project by themselves. You need whole teams of people with different competencies in order to make something work. And project time management and basically an ethical and professional approach to things. We have 3 programs in our department. It doesn't really matter. They all come off a common base. And the first 2 years of our programs are common in any case. But roughly speaking, electrical engineering is the electrical power and the energy side of things. We then have a mechatronics program, which is electrical engineering plus mechatronics. So a little bit of mechanical stuff. And essentially that would be things like robotics or electrical plus mechanical, but as seen from the eyes of an electrical engineer. And then we have electrical and computer engineering. These guys do a lot more computer science, and ultimately the place they end up is in developing hardware, designing hardware, implementing hardware, that side of things. So that's the extra skill. And I said hardware, but I guess software comes into that as well. All right, here's a tour of our building, a tour of our facilities. Fred Nichols. I'm the head of Department of Electrical Engineering at the University of Cape Town. UCT is a world-class university and we offer 3 programs in electrical engineering: electrical and computer, straight electrical, and a mechatronics program, which leans a little bit more towards robotics.
I'm Amir Patel. I'm an associate professor in the electrical engineering department, and I'm also the program convener for the mechatronics degree. The days of, purely mechanical or purely electrical systems are gone. So everything involves aspects of software engineering, and then also more recently things like machine learning and AI are becoming extremely prevalent and useful for many fields. Hi, my name is Yubir Gordon. I am currently doing my master's in wireless charging for drones. Renewable energy in general is just important for future generations, and it's important for the well-being of the planet as well. Using wind energy and solar energy as renewable energy sources, we can generate large amounts of power. We can use this to power households and even charge electric vehicles and electric bikes.
My name is Kuko Kushe. I'm here at UCT, studying towards a master's degree in electrical engineering. I finished my BSc in mechatronics in 2019 and I started my MSc this year. I believe over the past 4 years, my degree at UCT was honestly one of the best times of my life on an intellectual perspective, because if I wanted to build something, there was always someone who could help me, and there were resources in the university that I could utilize to actually get to that point. The biggest motivator that is important that's actually going to sustain you is following what you're interested in, because that's what's going to last, and that's what's going to give you direction.
I'm Trevor Gordon. I'm an emeritus professor. The students are exposed to 100-year history of electrical engineering in ways that reflect what's happening outside in the real world. And I think that gives a lot of opportunity for learning.
In terms of the equipment, the department has everything in terms of the machines that you would need. We are given free rein to try out many ideas, and the cool part about that is I may have an idea and not know where it's going to be, but the university will facilitate how we can turn that into an innovation which will benefit society.
I'm very, very, very proud to be part of the city.
Thank you for attending this presentation. We look forward to seeing you in 2021, and we wish you the best of luck in your examinations. I guess that should have been, we look forward to seeing you in 2022, but we look forward to you applying in 2021. Right. I think that's all I would like to say. I'm going to exit the presentation and just see if there's any questions that I can take. I'm just looking at a handful of questions, and I think some of them have been answered. Is computer engineering also offered separately in the university, or is it a part of electrical engineering? The answer is our computer science department has something that they call computer engineering. They're not actually engineering, and they're not accredited with the Engineering Council of South Africa. So they do elements of engineering, but they wouldn't come out qualified as something that is a mobile engineer that can operate anywhere around the world. How long can I study for electrical and computer engineering degree? All of our degrees are, in principle, they can be completed in 4 years. It's fairly common that they won't be completed in 4 years, and students sometimes take 5, and when they start taking 6, then we feel that they perhaps are taking a little bit long. But the default is 4, and I think about 35% of our students will finish in 4 years. What is between software engineering and computer engineering? The emphasis, we make sure that our computer engineers are capable with software, but the emphasis is really on hardware development and design. So that would be designing embedded systems, designing high performance computing systems, designing bespoke computers that can do things that you can't really buy off the shelf. So an example would be the SKA example that I gave earlier, where we need high-end computing. Basically, they call them, most of the devices are correlators. Very particular computing devices that you can't buy, and you need to build those computing devices to do some particular application. So our EC students would be able to do hardware design and hardware development, whereas typically a software engineer is only going to be able to do software design. What is software design? I guess it's got to do with design patterns and templates and ways of doing things in a software environment. Whether that should be or could be considered an engineering application or an engineering discipline, I guess you could question. Is it better to do software engineering or computer engineering? It depends on your interests. If you think that pure software is what you're interested in, then I guess software engineering is the thing for you to do. If you think that computers as devices are interesting things, then you need to be able to do hardware and software. And typically a software engineer is not going to know anything about hardware, and particularly not bespoke hardware. I'm just taking a cross-section of questions. I believe I've only got 2 minutes left, and then this feed will cut off. So, is the computer and electrical engineering internationally accredited? Definitely. Every single engineering program at UCT is accredited. They're all mobile. They're registered with the Washington Accord, so you can take your degree anywhere you want to. There's no difference between a BSc Eng and a B-Eng. They're the same qualification, they just have a different name. All right. So I'm just going to wrap up quickly just to say, my view is that electrical engineering is a future-proof discipline. Of all the engineering disciplines, it's the one that is most moving the fastest at the moment. There's a lot of things happening. The whole world appears to be moving in the direction of automation and sort of intelligence, and electrical engineering is the one engineering discipline that really concentrates on that. So I think there's a YouTube video called What Do You Do as an Electrical Engineer? It's a fascinating video to look at. It's about 15 minutes long. They've got one for mechanical engineering as well. So if you want more information, take a look at those. Anyway, I thank you for your attendance.